All right. Hello, everyone. My name is Christoph Waldmann. I'm working for IEEE Oceanic Engineering Society, and I'm the chairman of the OES Standing Committee on Standards. That's something that I have on my mind for almost 2 years now. And so today we will have a session on AI methods in ocean sciences from different perspectives. We have four speakers, including myself, and this is Sage Osborne, Douglas Rao, and Henry Rule, and who will provide their perspectives. And after 1 hour, after these four presentations, we enter a discussion phase, and I hope we have some lively discussions going on. And yeah, first of all, I would like to thank you all for joining, and then I give a short overview, or at least my perspective. Yeah, very simple. We are seeing this rapid development going on in the application of artificial intelligence, and it's in different domains. And sometimes I have the feeling in ocean sciences there could be a more widespread use, and that's one of the reasons why it's good to have this session and have a discussion on that. And so, what's the specialty? We already have a lot of methods around to analyze data, but the particular ability of AI tools to process large amount of data in an efficient way is a special aspect that we have in mind. Yeah, and the complexity of environment data is really challenging, and it's an obstacle for professionals to overcome. Yeah, let's see. Okay. Here comes the first example. Just 1 week ago, there was a workshop, Marine Imaging Workshop 2024 at Mbari, Montreal Aquarium Research Institute. And as you can see from the program, here's just two presentations that have been given last week. Machine learning plays an important part of that. And we will hear more on that from Henry Rule, who will give a presentation on that. But in the end, we can say, yes, we already are using it. So what else shall we do? So there's a lot of people who are making use of these very efficient methods. Here's another example from image analysis, pattern recognition. So you identify certain type of fish species. This is actually a European project and European installation where they have a camera running, and then the fish species are recognized by the camera system together with an AI tool. Okay, so, but I believe there is still some potential in other domains that has to do with time series data. Again, I just took out an example. There are hundreds of them, I'm pretty sure, that could point in a similar direction. But in this case, we have people who are applying AI methods for sea surface temperature data. And there's a typical process change that you see here: data pre-processing, models, experiments, and analysis. And usually you, a more classical approach, you probably will not have such a careful look at all these different steps. But as AI models are mainly data-driven, all these steps are very important to keep in mind. And I think Doug Rao and Sage Osborne will tell us about that, what the constraints are, how we should look at the quality of the data, and what other constraints we should impose on the methods. And what you can see here, there are different comparison between different methods. METFE is actually, so to say, classical model of the Mediterranean Sea. And the other are neural networks, random forest, and LSTM method, which proved to be very efficient, as you can see here. If you look at the y-axis, which is a random mean square error, it seems to perform very well if you want to come up with more forecast for heat events, heat waves in the Mediterranean Sea. Okay, here's another example, which I like a lot, but then, that's just as an introduction. There's a company in Woods Hole who has developed a service, and that has to do with precipitation rate. And what they do is they look at the sea surface salinity anomaly in the Atlantic Ocean and then make prediction on in certain regions of our world. So they compare these patterns and then make a prediction on precipitation modes, as you can see here. And there's a delay between these two, say on left-hand side with the sea surface temperature anomaly, it's about, say, March to May, and then the precipitation is forecast for time frame June to August. So they make a long-term forecast, which usually is very difficult to do. Machine learning is helping here. Yes, you probably know there is a different approach that we take if we use this AI method. But we have to keep in mind there is something with our environmental data. It's not just ocean data, but also meteorological data. They are suffering from large noise, non-linearity, and non-stationarity. That makes it very difficult to work with classical methods. They often cannot address in a proper way the complex dynamics, in particular also the nonlinear patterns. So here's just an example of a Gaussian process. In the end, you take a different approach. You have more or less agnostic approach, and then put up some constraints, and then select certain type of AI models, like in this case, Gaussian process. And this is then connected to the constraints that we will going to hear later on. Yeah, why is this important to emphasize? Machine learning are very attractive, they are very efficient, but often just task-specific and lack generalization. And the other issue which makes it difficult for many people to accept this is their opacity and limited interpretability of what can come out of these methods. So people are very skeptical about this, but in particular if it comes to verification and validation. So how can we how can we go ahead? We can probably think about best practice and standard to develop, and by that help people to find the right approach and help them also to validate and verify whether the way how he is going through all the steps is really compliant with what other people have done. So one thing that I would emphasize is to what degree can AI methods be tested. So I think that's very important to keep in mind. And yeah, we also have to think about procedures, how to check AI methods against each other. Yeah, as I mentioned, I'm coming from the standard side, and so standards is means a lot of work to go through all the details that you need to know and that you keep in mind. And typically, it's not just a single person, but you have a group of people who say, yes, we would like to think about this and come up with ideas on a concept and structuring this process. And it's not probably just domain scientists. We probably also need people who experienced in data science, system engineers. And, it's not just the observation networks, but also the modelers who have to get involved. So it's a huge task because, as I mentioned, there's some skepticism and it's not very easy to validate and verify that. Yeah, I mentioned already machine learning is data-driven, and there are specific challenges if you talk about sanitization, and here's some of these topics listed. And yeah, data preparation, as I've said, model training, this is something new that you don't have to go through if you use more classical methods. And that's a specific challenge if you talk about best practice and standards. By the way, everything is open for discussion. If you have a different perspective later, let me know, and then we will take notes and then also start a discussion on all that. Yeah, let's skip that. I think I don't want to take away too much time because we will have some more time. We need some more time for discussion. I just come to the conclusion And this is what we need is a requirements framework. So the requirements on the AI techniques and the special features, and some are listed here. Again, I would like to emphasize data quality and representativeness. And connected to that is also the so-called uncertainty, which is something that is not very well designed, something that you need to know and that you have to think about very carefully. And I think that's a particular aspect that you usually don't find in other domains. This representativeness is something that tells you something about what you already know about the processes that you can expect. And that's very difficult to grasp. Yeah, let's see. From my point of view, it would be good if we also could enter a discussion. Doesn't have to be today, but some other time, if we can establish some sort of group of interested people, then we probably will go to all these processing steps. And again, I would like to emphasize, I see real need for this first process, data pre-processing process, to think about these best practice standard. But again, it's up to discussion, and I will be happy to hear your views on that. All right, so that was a quick rush through what I wanted to present, and I'm happy to answer any questions. So thank you very much. I stop here the sharing. Any questions? Quick questions that you would like to ask? Maybe it was too fast or too condensed or trivial, that people already agree on that. All right, so if not, then we can continue. I think, Sage, you are next on the list. Is that right?
I think we have a raised hand. We do have a raised hand.
Raise your hand. Sorry, yeah. Let's see. Please go ahead and ask your question. Or do I have to go into the chat? Here, chat. Maybe what was my connection? Can you see the question, Doug?
No, I just see a raised hand from Stephen Holt, and I think there's a Q&A functionality in the webinar, and so if you want to go to the Q&A.
Yes. No open questions here on my side.
Yeah, I think maybe Stephen need to put that in the Q&A tab first before we can.
Here.
Right.
It's in the Q&A. Okay, Ingrid Puya has asked something, but I can't see it. Can someone see it? Here's a chat. Ingrid, maybe you can just put your question in the Q&A again. And right now I can't see your question.
I believe he has been elevated as a panelist. So, Stephen, can you unmute yourself?
For ocean monitoring. Okay, that's a question from Are You on the Couple? And so I could say something about time series data, but Sage, could you try to give a brief answer to that? AI for ocean monitoring from your perspective. I think you deal with salinity and temperature data, and probably will say something in your presentation. But is there any?
Yeah, I'll go into a bit more detail into a method I developed about to deal with ocean monitoring data.
Right.
In general, you have a couple of issues related to that, right? There's the different sources of uncertainty as well as sort of natural fluctuations that you see in oceanographic data. And in principle, there's, we're dealing with like an open thermodynamic system. Sorry about that. So you're going to see a lot of variability that isn't due to the immediate region that you're monitoring or may not be represented in your data historically. So you have to expand your methods to be able to incorporate those kinds of effects or to be able to handle those kinds of effects reliably.
I see now the question of Ingrid. Do you think we can already elaborate a model with AI for climate change and detection of tipping point and time series? So I can say to that, in meteorology, they are using already AI methods. To what extent they can use it also for long-term predictions, so over years or decades, I cannot reply, but I know that they are using AI methods in parallel to their more classical methods, and they are again showing very good performance. So I think that's a good question, but very hard to answer right now. In any case, I think Sage will now give us a print. Can you share your screen, or shall I present your slide?
Share screen.
Okay.
So 1 second. Listen. All right. Can everybody see my slides, or can someone confirm that they can see my slides?
Yes, we can see your slide.
Perfect. So yeah, like I mentioned in answering the last question, I'm going to try to talk a little bit about this method that I've developed for handling uncertainty in oceanographic observations. The application area for this is on the order of uncertainty quantification, but also related to data QA and QC, or quality control, quality assurance, and how we can do that with multiple observations or in time series data. So just to sort of set the stage a little bit, in situ observations are largely what I'm talking about. And so these, sorry, 1 second, a guest. Anyway, so there's a lot of natural variability in these data sets, and they vary in some cases minute to minute. And as you can see, as it sort of traverses over the ocean, you have some large fluctuations. Similarly, on this right time series, as we collect data, the mean and the variance of the time series are going to vary quite a bit. And this isn't just due to natural fluctuations in the water parcel or other kind of like fluid subsetting. It's also due to obvious things like weather effects, water masses, and flows. And so, doing a sort of typical analysis isn't really going to cut it if we wanted to actually do some uncertainty quantification on these time series. So the way that we think about it is as a stochastic process. So if your water parcel is some sort of representative of some subset of a probability space, as you traverse the ocean, you're essentially drawing from that. And so we're going to try to see if we can figure out what the probability distribution for a particular time point looks like, and then forward some data that we've collected, determine if it's likely that that data belongs to that probability distribution, so that we can identify whether the sensor encountered any kind of erroneous behavior, hit an iceberg, ran over a jellyfish, that kind of thing. But this is also complicated. This, like I mentioned earlier, it's an open system. We have a lot of turbulence in the system, and the noise isn't going to be evenly distributed. So it's going to be anisotropic, it's going to be non-Markovian. And so assuming something like a Gaussian distribution for each of these data points isn't going to be representative, right? The ocean has memories. So as we observe these processes, we're going to see correlations farther back in time than you normally would in other more simple statistical processes. But we do have some, information what we can go on. We can look at the sort of governing equations for each of these systems and say, we know what the relationships between these variables are supposed to be. So rather than going in blind and looking at just one variable, we can look at multiple variables and say that, if we believe that in some sense that there's a probability distribution associated with this observation, then the correlation structure should also reflect these physical principles. And in that case, we actually have something to go on, because no matter what instrument is being used to make these observations, the these equations will be true everywhere. So if we can capture this somehow, right, then maybe we can generalize to other kinds of observations, other observing systems, other variables, by using that cross-correlational structure. And so we have this sort of joint picture. We have this that leads us to a SPDE, or stochastic partial differential equation, for multivariate noise, well, system of equations, I should say. All I'm trying to convey in this slide, if you're unfamiliar with this mathematics, that's not the important part. The important part is just that we are assuming there's some base level of fluctuation associated with each variable, and so that the stochastic component and the deterministic component are contributing jointly to the evolution of the system. So before we go about formulating a deep neural network, we're going to need some data. And in order to ensure that we're accurately representing the equations that we want, or the evolution of the system due to those equations that we want, we do some numerical modeling to generate some synthetic training data that we can then test so that the model has accurately learned to represent. So we start off with some anisotropic random field and advance that forward in time jointly across all of the SST fields, velocity fields, et cetera, in order to generate those noisy and memoryful correlations. And we can do two things with that. We can do the sanity check and say, okay, our field evolution, as we subsample that in time, so in this green arrow, right, in situ time, we're traversing this system or this simulation with some kind of observing vehicle. You know, does that create or recreate the same statistical behavior as sampling? And similarly, we can then subset and say, okay, we have this grid or this stencil, and then we have some set of field values. And so with this set of, what this is saying is, what we're going to design this neural network to do, right, is take this stencil or this grid and predict on the grid for the next time step given some input data. Right, so that's going to be the goal for this neural network. Before we get into that, one more thing that's used to design this neural network is this idea of a tensor network, which is a way of decomposing operators and fields into local sites, which you then contract over these lines. So the connected lines are representing summation. And this sort of lets us look at the dynamical modes associated with that prediction. And so we're not just throwing any neural network configuration or architecture at this problem, we're actually deriving it from these, or at least associating it and approximating it with these modal expansions.
Sage, I think we're only seeing the slides number 2 on our screen. Maybe you're advancing it.
Oh, you haven't seen any of the slides?
Unfortunately, no. Yeah.
Okay, so you see this? You don't see this?
Nothing's moving.
Okay, well, let me try again. I'm so sorry. Okay, are you seeing this?
Yeah, we're seeing a network structure.
Network structure?
The parcel of parcels, right? This parcel select. Yeah.
Okay, and are you seeing the two square diagrams?
Yes, we are.
Yeah, this.
Okay. Okay, I apologize, everybody. Let me back up. Okay, so I said a little bit about, this is the slide that I was referencing when I was talking about the joint probability space. So I'm just confirming that this is actually. I was booted briefly.
Yeah, if you can reshare your slides, I think your slides is gone.
Okay. So revisiting observation as a stochastic process. We treat these sort of fluid parcels as probability spaces, or as sets of probability space, as I mentioned before, and sampling that sort of creates your time series until you have this correlation structure that I mentioned. Are we seeing the observing platforms slide now?
Yes.
Yes.
Okay, thank you. So again, as I mentioned, we have turbulence. We have, as we make these observations, they're related to each other in more than just a time series or a trajectory. There's some dynamics going on as well, and so that influences what that probability is going to look like. We have physical system equations that deterministically evolves those properties as well, and those things are going to be the same everywhere, which creates this dissipative open system, right? So things flow in, and then you might not ever see them again. Observations can be totally unique, but at the same time, we still want to be able to relate them to each other because of that correlational structure. This is the slide where I said you don't need to be familiar with this math, but this joint evolution is sort of the point between the stochastic and the deterministic components. And so then this is the simulation slide. So I'm assuming that you can see this, and so starting from the left, we begin with some anisotropic distribution, some sort of like random. We're not making an assumption about what's actually happening in the system. We're just going to evolve it in time. We subsample that into a local coordinate system or a super local coordinate system, I should say, and that corresponds to the resolution of the sampling and some field values. And so we're going to use that. We're going to predict on that stencil to the next time step for those field values. So diagrammatically, we think about this in terms of a tensor network, which is that decomposition that I mentioned. And so then we have some tie between the neural network architecture and this physical system. And so more explicitly, what we do is, so these solid blocks are representing those field values. The empty block represents that coordinate system, and then you have some diagram for some starting initial distribution. Right, so all of those are sort of fed into the model, which the initial activation forms some feature identification, which we populate. We use to populate these networks, which will then predict out both some evolved distribution from the past distribution as well as the new field values onto that specific sample. We compare this against the numerical data, the Wasserstein distance between the observed distribution or the true distribution and the predicted distribution, as well as the data, the real data. These networks, because they're actually, the components do correspond to dynamical modes, we can start to test different combinations of those modes in this sort of like larger state space in order to determine what the, give me 1 second. Apologies again. In order to identify these interactions between the fields, where these things are interdependent, and so their joint evolution can also be modeled. So to test it, we can try to validate the accuracy of these predictions using, on this left side, the numerical solution data. So on this top column is the data that we synthetically generated. On this second row, the predicted values, and then the relative error between them on the bottom. And that shows some relatively decent agreement for this subsample of data, at least. We can also look at the fine-tuning data. So this is Saildrone 1060. This is an uncrewed surface vehicle, and what this is showing is this fine-tuning on data that was collected in the varying sea. And we see, again, relatively low relative error. And again, we could test the generalizability of this with Saildrone data that wasn't used in this fine-tuning step. So this is a completely different geographic region. So we're testing, can we actually use this apart from data that we've seen already, right? Because if observational data models like this, in my opinion, won't work if you can't generalize them, right? And I mean, there's really not so much my opinion. This is the fact that the ocean is chaotic and variable, et cetera. So, and we can see that we have relatively decent agreement in the relative error there as well. And these are all SST, by the way. So then the next thing that we want to do is try to characterize these erroneous data points. So we take this uncertainty quantification, we turn it into essentially the Wasserstein distance between the distribution of the data as it's collected and the predicted distribution of this neural network, right? So we're taking advantage of this probability distribution that it's predicting. And so we have two models. On the left, we have a model for the seawater. It's just SST, SSS. And on the right, we have atmospheric temperature, relative humidity, and barometric pressure. And so I'm gonna zoom in on two time series just to make this a little bit more straightforward. So you can imagine you get this time series data in strict values, right? And you don't really know anything about it. And so then we apply this uncertainty quantification comparison to these data, and we see that there's some sort of signal that's being picked out of this data, right? And yeah, and you can probably eyeball this and say, well, clearly something has happened in this observation, right? But we've also identified it, or we've identified something, and it seems to correlate with our idea of that. And there's a couple of things that we can say about this, right? So first of all, this is a multivariate representation, and we can see that data points at roughly the same times are all being treated similarly, right? So we have this sort of observation by observation accuracy. We can see that it's not perfect. There's some impact on the scoring, or this sort of determination of whether these data observations are likely, that's being impacted by this other signal. But we can also see that that impact carries across both variables. So the reason that we chose this data as an initial testing point for this method is that it already was flagged by an oceanographer. And so as the scheme that they use is relatively simple. And in this data set, we effectively are dealing with two flags, two on this left side of the color bar saying that this data is acceptable for free use, modeling, et cetera. And then 5 being this data is not particularly acceptable. So it's a relatively straightforward metric in this case. And we can see already that there's some close alignment between those things, but we can do that for all 10,000 data points in this sample across. And for these two variables, we see that there's pretty good agreement between the two of them, right? So we picked this arbitrary cutoff of 0.3, and just to sort of be able to translate this uncertainty quantification metric into the flagging scheme. And then, this obviously varies depending on the sensitivity to that metric, but there's quite a bit of a wide difference between them. So on this top right corner is our false positives, and then we have our false. We don't actually have any false negatives in these predictions, so they're relatively satisfying results. And then one final test, because we want this to be extensible, we want to show that this is extensible to other systems. We take this data that was collected during Hurricane Beryl last July, and so this was an attempt to measure hurricane force, winds, etc., using one of these drones, and we were able to ingest this data in a sort of a live feed and run it against this model. And we see two things. My favorite thing is not so obvious about this plot, which is that for each of these spikes in air temperature and relative humidity, we are not seeing really high differences between the model prediction and the distribution of the data itself. So in other words, the change in conditions due to the hurricane did not cause problems with the model, and it's happy to do uncertainty quantification for those rapid changes. But it did pick something up in the middle of this hurricane, right? So and then we could see that there is, we can zoom in on that there is some kind of a sensor failure going on. It's not perfect. I would say we have some tweaking to do, but because we've developed this with this physical principle in mind, that should be relatively easy to extend. So I'm happy to take any questions, but I think I'm probably over time due to the issues and things like that.
thank you for a very interesting presentation. We will come back to what you presented in the discussion. I'm pretty sure there are some questions to you later on. So thank you very much again, Sage. And then we go on with Doug. So are you ready to give your presentation?
Yes, I am. Let me start
Great.
sharing my screen.
Thank you, Doug.
All right. Please let me know if you cannot see my slides. And thanks for the invitation, Christopher, on this session. And today I'm going to try to present an effort that we are working with the community on the community standards for the AI-ready open environmental data. And I'm joining you from Asheville, North Carolina, and I'm with NOAA's Corporate Institute for Satellite Research Studies in Asheville, North Carolina, and also supporting NOAA Center for Artificial Intelligence. And so just briefly showing some of the examples that NOAA has already been using and enabling AI, from the rip current prediction to ecosystem monitoring in the marine ecosystems, as well as space weather forecasts and numerical weather prediction, as well as issues like the wildfire and across different mission spaces that NOAA has. And that is really supporting the advancing the mission of NOAA. And on the other hand, the NOAA also trying to enable those AI applications through those AI-ready data and building a community practice and providing those open available data for people to monitoring and in ocean and atmospheric conditions. And with more than 60 petabytes of data, that NOAA's data has been used in many different AI applications. And one of the example, like Sage was showing, the sail drones and all those uncrewed systems are a great example of those data can be used to enable some of the monitoring in the extreme conditions. And so with NOAA Center for Artificial Intelligence, that we have different focuses. There are 4 major areas. One is the training of the workforce on the responsible use of AI, and the other side is the AI-ready data standards, which I'm going to talk more about specifically in this presentation. And we also focus on the partnership engagements. One of the flagship events for us is the workshop that happened in September. We this year focus on heat resilience. There's also a lot of discussion about marine heat wave and impact on ecosystems during the workshop in September. And instead, we are trying to coordinate community practice coordinations with close to 1,500 members on our mailing list, and the lists are also growing. And really trying to enable the innovation of ethical and responsible use of AI for NOAA missions, as well as with NOAA's data. So more specifically about AI-ready data, and so this is a paper published by Google researchers in 2021 discussing the technical debt and data cascading in the AI systems, where on the figure it shows the impact of the data going across from upstream to downstream of AI application development, from the problem description to data collection, all the way to the training, evaluation, the deployments. And where they really emphasize that the compounding events can cause those negative downstream effects from the data issues that can really resolve those technical debts over time. And those impacts are usually negative and sometimes can cause really significant impacts. And those accumulation of impact is why we are really interested in how can we make the data better suited for the applications in a responsible and ethical way. And the first thing we need to do is to understanding the needs of the users who are using this data for AI applications. And so that's why we are looking at what's so-called AI-ready data. And in the left side, on the left side, you will see a quote from the book Deep Learning with Python. That's one of the most popular package keras in Python for deep learning, machine learning and deep learning. They emphasizing the data accuracy, cleaning, and annotation are really important, but the book really specifically focuses on the coding and then really leaving the data preparation as an exercise for the readers, which is less than ideal. And so as people who are interested in data management and promoting the use of data, we looked into how people are using those data for applications. And in one of the survey we did, with more than 100 people responded. On the right side, you'll see people responded. At least half of the people said they spend at least half of their time on data preparation and analysis, processing before they can really feed those things into AI development process. So through a community, the Earth Science Information Partners, which is a group including public sectors like the federal agencies within the US and other international agencies, like members from Met Office and other international partners, as well as private sectors and academia, that we are really looking at how can we leveraging those data professionals' expertise to advance this specific idea of our AI-ready data. And so with this initiative that we define the AI-ready data with 4 characteristics. One is documentation, which like really enables the users to understand the content of data set and increase the data usability. And quality of the data is to determine the fit for purpose of data sets for AI and applications, as well as that can really affecting the trustworthiness of those AI applications. And for the access piece, that really emphasizing the efficiency and reproducibility of the AI and research and development process. And for the data preparation, that really help us to, as a data management professionals, identify those common data services and tools to really reduce those pre-processing burdens for our users who want to use those data for the AI applications. And so that we publish our checklist on the GitHub repository on the slides, and you can find those most recent information. And we are in the process of working on our next iteration of the checklist updates. And a little bit more details, for example, in the data quality side, that it describes the definition of the completeness and how to assessing those completeness of the data sets, the consistency and the bias or unbiasedness of those data sets. And for some of the real-time applications, timeliness can be an issue for users who want to choose the right data for their use. Right, uncertainty and provenance is also important for the trustworthiness of those data sets. And for the documentation, that really the basic standard common metadata is the foundation. But then there's additional questions we ask the data providers to assess whether they provide tools and examples to use those data, and is there any data identifiers and license information about those data. For the data access, really looking into the data formats, delivery options, as well as the security and privacy concerns, especially in some of those use cases. You might have those sensitive information, for example, endangered species that you don't want to immediately give out, and unless that people have the right access to those data. And for the preparations that really help identifying those common requested features or common requested services, like the labeling, the labels or targets, the recommended data splits and the outliers, have those been identified for people who want to who only use those normal data for their case. And I think the current efforts it's really aligned with some of those like communities' efforts on FAIR principles implementation and other things. But there's additional things we are asking, like the quality is one thing that FAIR principle currently couldn't address to the most extent. And so with AI data, we create a checklist, like I mentioned, that had already been published on the GitHub repository, and we are planning for annual updates going forward. And to align with the checklist, we have a template for people trying to use that as a way to go through your own data sets and see if there's any specific areas that your data set can be improved based on the recommendations, guidelines that we created for the AI-ready data. And there's some of the pilot projects that NOAA Center for AI has been funding and working with communities to do. And SAGE and their team has been working on the QA/QC with uncrewed systems. And then there's also the World Ocean Database that is produced by NOAA's National Centers for Environmental Information. It's another data set, a pilot project we're working with, specifically looking at in situ data. And there are other more completed pilot. This is one. The first phase has been completed. That's tropical cyclone data combining those like best tracks and then different satellite observations as well as the model reanalysis data to create a data set that can really help people to improve tropical cyclone modeling as well as the tracking and intensity estimation with that. That have already been published through the NOAA Open Data Dissemination Program on Amazon Web Service, and also will be archived through the NOAA Data Center in Asheville. Another project is the water column sonar data, and this is working with Carrie Wabel in series in Boulder, and then that data set are also already being published through the NOAA Open Data Dissemination Programs, that they created a series of notebooks trying to help people to better use those water column sonar data in their ZAR store for those data sets. So with the AI-ready data checklist, that we have a manual assessment workflow where from the data centers or data managers that you can select specific data sets and to do those manual assessments based on checklists to create the assessment reports. And it's really helpful, and we have heard that feedback for data who are creating the data that help them to think about how they prepare the data set from the beginning or how to improve it. And that can, but it really requires heavy involvement in the assessments. And based on a few of the efforts we tried with different data experts, it really takes about 45 to 60 minutes for each assessment of a data set. And that can really hard to be scaled to those like 60 petabytes of the data set that NOAA has in the data archive. Right, so that what we are looking at as well future AI readiness workflow is that with the documentation that associated with the data sets in a data center, we have been currently exploring the natural language processing tools to see how much we can automate assessments parts, because some of those things, especially when you have the right metadata, you can really automate a lot of those informations and to help us to accelerate those assessment workflows and identify the improvement that can be made to a specific data set when the resource becomes available. And so I'm going to close with my presentation. Close my presentation with this one slide and looking at the different 4 areas we're looking at with AI-ready data. Really, first of all, the community standards and guidelines that is very fit for this workshop discussion on the AI-ready data. And then the second part is to develop those automatic assessment tools for those assessments to help the data centers guide the improvements. And the third part is to improve those data sets that people may have, especially thinking about how can we use a specific topic or use case to create a collection of those AI-ready data for those environmental data. And I think some of the examples, I'm really excited to hear about FlatNet example that is going to come up next. And then also I want to emphasize the engagements and sustainability in those engagements with the users, and also help the users building capacity to use those AI applications with those data sets available. And with that, I'm going to stop here. I'm happy to take any immediate questions if we have any.
Thank you very much, Doug. Very interesting, inspiring presentation. No immediate questions. I would have some, but I postpone it to the later discussion session. Will you be around later for the discussion? All right. Perfect.
Yeah, I will.
Okay, good. Okay, Henry, it's your turn now.
Hello. Slides going
Hello.
Here. Right. Okay, is that coming across okay?
Yes, looks good.
All right. So first, I'll tell you a little bit about the deep ocean observing strategy. So Patrick Heimbach is the lead investigator for that project. Leslie Smith does quite a lot of the work to coordinate it, and there's many others involved, including myself, the co-PI of the CellNet project that helps fund the efforts. And so, yeah, the Deep Ocean Observing Strategy is a project of Goose. It's also affiliated with the UN Decade for Ocean Science for Sustainable Development as a program. And it's a a network of networks in many ways, and so it looks to be community-driven and align strategy and activities towards achieving, many of the things we talk about in the UN Decade for Sustainable Development and these things, and sustainable blue economy relevant to the deep ocean and things like that. And so it bridges across disciplines. So it's really trying to connect physics, biogeochemistry, and ecosystems work and biology in the context of Goose and bring more deep ocean scientists into the Goose context. So there's a lot of facilitation across various groups. And one of the main things that makes it work is this deep ocean early career researcher network called DOERS. And so this effort has really been the magic of what makes the DOERS program work well. So there are many examples now of early career folks being brought into, sort of coordinating roles or brought into networks that they might not have otherwise been brought into as an early career researcher. And so being part of working groups and strategic teams and expert panels and so on. And it really is adding the needed capacity that we need to make progress on deep ocean science and these things we all know about. So we've had now 3 virtual meetings, and so these are great because they can be really inclusive, like the meeting series that we're participating in this week. And it has one in-person meeting so far at Scripps Oceanography in California that brought in many people together to work on various tasks, and to include a mapping exercise, for example, where people were able to work with experts from Esri, one of the leading mapping companies in the world, who made their software and tools available for free, as well as lots of shareware code to work with together. I'll come back to this meeting series at the end here. So there are several working groups with DOERS that are active. There's something around essential ocean variables. I'll talk a little bit more about what those are. Accessible ocean technology, so like thinking about low-cost tech, for example. There's also things like habitat mapping and modeling and getting science into policy, and also seafarers, which is another form of early career work, bringing scientists onto vessels. So the essential ocean variables is a concept that's established by the Global Ocean Observing System, and it really is firstly a tool to identify what things are a priority to measure across physics, biogeochemistry, and ecosystems work, and then some context around what those measurements are and what they can do for society. But what's happening now is there's a whole layer of implementation work that's being done. So developing data schema examples, and more strategic guidance for implementation. And I work on the Goose Bioecosystems panel. And you'll appreciate that imaging and AI tools can feed into almost all of those, really all of them. And so there's a lot of promise in developing AI to meet the needs for ocean information in the context of the Global Ocean Observing System. And so that kind of need drove in part the establishment of a project or program called FathomNet. It's been also known as Ocean Vision EI, but we're now sort of transitioning into the FathomNet brand as our overarching brand for this work. It was funded in part by the National Science Foundation Convergence Accelerator, and so there's been a lot of sort of human-centered design and co-design that's gone into the things that you'll hear about next. It's led by Kakani Katija colleagues from around the country, and indeed around the world, with Europe and folks in Africa previously contributing to what you'll see. And there's several philanthropic sponsors, including Schmidt Marine, Dalio, Mbari contributes a bit, and then the David and Lucille Packard Foundation. Okay, so we know the challenge basically. We've got visual data, we want to do some AI work with it, and human verification is a big part of that. We've heard about some of the issues with, the environment changes over time, so we shouldn't expect our models to work well in new conditions that the model hasn't worked in previously. And that human verification is a big bottleneck. All right, so what's our approach? So we've got a series of tools that work across, from experts to enthusiasts. Basically, the approach in FathomNet is across 3 pillars, and the first of these is this FathomNet database. And so this is as it says, basically a database where you can host annotations, for example. So we know that the labeled data is one of the most valuable things that we have in the world of artificial intelligence and machine learning, where we can use these for training new models, right? And so that there's this database that now anyone can contribute data to globally as a sort of a library, and you can also pull images from this library to make and improve models that you might be working on. And there's also a model library that goes with it. And we also have an agreement now with NOAA and CEI to host image data, so that these image files you might appreciate if you're working in this field, that it's very, very helpful to have a permanent URL associated with the image for onward use of this in modeling and code development. And so we now have an agreement with NOAA that can move some of this sort of context from university labs and personality-driven sort of environments into something that's a bit more stable over the long term, beyond any single person's career. What's next? We've got this portal in development, and this is really kind of a production space. So this is where you can upload visual data, you can annotate it. There's both public and private repositories, and you can develop machine learning tools here and use them. So you can run models in this environment. So again, it's sort of a production space. And it's just undergoing its sort of final beta testing over these next months. And the third piece is what's called FathomNet. So this is a game, and it's really focused firstly on sort of enthusiasts, basically people that are enthusiastic about the ocean, animal lovers, armchair explorers, and so on. And then there's various levels of the ocean science community, so the underserved communities, people that might not have access to imagery otherwise, high school kids, and so on. And so that there's a variety of folks that this can serve. It's available now on iOS and Android. And it's really kind of started to spin up very nicely. So there's lots of folks using it now. About almost 6 million annotations since May. And there's now convergence. There's a convergence sort of tool that's built into this framework where the convergence can build confidence in the AI rather than the community annotated instances. And so there's real knowledge coming out of this. That's sort of the complete pipeline there. And you can see there that there's potentially a lot more information that can come from this game than can be done through these other means alone. And so how do these things fit together? So I'll just kind of scroll through these steps here, get to the key part. So these 3 things are interesting. They each have their own purpose, but really the magic here is that there's a content management system that goes between them, so that if you upload new images, you can have them go into the game that are unannotated. They can come back out with some label information. You can use that in new production of information from models, making new models. There's quite a lot of flexibility in how this can work and capacity. And this is sort of a reimagining of that sort of connectivity, but from a sort of a human standpoint. And so that there's various audiences for this. And this is really an outcome. It makes it more complicated to explain and to run, for sure, having these 3 pillars. But they really were developed based on that human-centered design work, that talking to people about what they need and what they want, and from a variety of perspectives. And so that's how we arrived at what we're showing you today. But really what's I think important to remember is that in the context of the kind of meeting we're having today, is that we're looking to get information into the Ocean Biodiversity Information System. There's a dire need for biodiversity information. There's organizations that exist that can help guide how to do that. That's Goose and the meeting we're in today. And the biodiversity and ecosystems panel, for example, has just doubled its size so that it has more people that can help communicate the sort of ins and outs of how to work with biology data. And then there's Marine Life 2030, which is helping to organize information in teams to deliver against the needs of the UN Decade for Sustainable Development for ocean science. So let's see here. Right, and so coming on to some little practical points. So we have these working groups in DEUCE, and Christoph and others have now sort of spun up a working group that we could continue and sort of solidify into this DEUCE framework. And so I think that's kind of pushing on an open door. And so I hope we can continue with that. And just before I go to that, so that there is a meeting, the next virtual meeting will be in May of 2025. And we could have a session there that could be 2 hours or longer, that can be virtual and inclusive, where we can continue to have the kind of conversation we're having today, dig into some more examples and technical points, and I'd be interested to hear about any strategic planning documentation that might be coming out in the next 6 months that could help focus that discussion. And this isn't a deep ocean example, but I just wanted to quickly give an example of operationalizing AI in our region. So I work in the Central and Northern California Ocean Observing System, and we work closely with our Southern California colleagues who have led the development of this imaging flow cytobot network in California. And this has turned out to be a really powerful example, I think of operationalizing AI tools, where we have these underwater microscopes throughout the state, and they deliver hourly information on plankton biodiversity composition, and includes things like information for harmful algal blooms, which is one of the reasons why it was funded. But we can take this data and we can repackage it to provide generalized plankton data to the Ocean Biodiversity Information System. There's a slide from Stace Beaulieu at WHOI, who's helped with this, and some folks from our office, including Patrick Daniel and Fred Bard, who have developed an AI-based pipeline that includes scripts to translate the image regions of interest data points into format that's compatible with OBIS and compatible with assimilating into ocean dynamic models that include biogeochemical data assimilation. So coming on to the last bits here. So how can this work in an operationalized way? So this is still a research exercise, but we're trying to make it as operational as we can. So we now have a standard operating procedure for the microscopes for the region. We also have documentation for the models that we're using. The source code's available. We have publicly accessible endpoints to visualize the unclassified data, as well as the classified and sort of value-added data on the types and abundances of plankton as we're seeing them. And so this is really sort of, I think, what I would like to see more of anyway, sort of documentation so that you build common understanding, ultimately in trust, and then use is really what we first want out of these things. And so this is all happening in a NOAA certified regional association. So this is something where NOAA looks over our documentation and certifies what we're doing as sort of meeting standards and practices, so that this data can be considered federal for most intents and purposes. And so thanks for the opportunity to chat with you today. And I'll just reflect on the question about like what next steps should be taken to establish AI methods in a routine tool in marine science. And so I think some recommendation is to work with Goose and the related bodies to understand the value chain. So thinking about data from its starting point all the way through to when someone uses the information to make some kind of decision. And it's that latter sort of area of the value chain that often gets overlooked when developing technical tools. So, and there are lots and lots of people including on the line today, who work in Goose or with Goose in some way or another that can help talk through those things. And that's really that point of collection all the way through to the info user. And that, again, that documentation through to understanding trust and use. And those of you that out there that are interested in these tools, use them and get feedback on them. So there's FathomNet, but there's also many others. There's a BIGGLE, Squiddle Plus, Viami, and many more. And for ocean sound, there's tools like PyPam, Manta, so classifying ocean sound information to the occurrences of anthropogenic sounds and marine mammals and more, fish as well. So those are all out there. We use them and get feedback, and so we can build better tools. I'll stop there.
Thank you very much, Henry. Very good. And I actually have some discussion items, but first of all, I would like to ask the participants to ask their questions. And there's one from Sarah to you, Henry, about FathomNet infrastructure, also open for non-deep sea content imagery from space. That is very much not deep sea, but links to those habitats eventually. Plastic pollution, another keyword. Can you give an answer to that? You're muted.
Thank you. Thank you. We've been thinking about how we can expand what we kind of started with in terms of the image cases. I think we are open to probably any sort of ocean-oriented data. So that drone data, for example, could be, and then I think satellite images could also potentially be there. It is a bit, we want to be careful about not moving into a space that is probably best suited for others. So like full global satellite data sets are probably not the right place for us, but perhaps the higher resolution specialty cases of satellite data could be considered. Yeah.
Okay. Any other questions? Because otherwise I would like to enter discussion, and, you know, that's so to say as a summary from my perspective. I see, I think one important thing that all the presenters mentioned is that we have a new look at the measured data. So a more careful look, that's at least my impression. And if you work with, so to say, classical modeling, it's the observation data as a provocative statement, more just to say support this model or add some other aspects. But in case of AI methods, everything is relying on data, and it's a quality that we have to have a careful look at. And then all these other aspects like annotation, labeling, and flagging also comes into play. So I would like to hear from the speakers, and sure enough, also from the other people from the audience, their view on that. Is this a valid view on our discussion here, or does it mean any additional information? Let me know what you think.
I can attack that if that's all right.
Yes, sure. Thanks. Go ahead.
I think, well, an important distinction that you sort of implied is, or maybe something that's just important to point out for this discussion, is that all machine learning models, after they've been trained, are conditioned on the data that they were put in. So in other words, we usually think about it as the pipeline and sort of what the model has seen, and therefore what can it reliably work within. But I mean, I prefer to think about it as a sort of like a bound on when you can use that model. So in terms of incorporating or trying it out on new data, then you should have some kind of metric of how generalizable it is. It is generally my view. It goes beyond just do we have examples of this and it works. It's more, can we reliably say that we know these are cases that it's accurate on, and that comes with human in the loop applications like both Douglas and Henry talked about, as well as explainable methods where you try to identify components of the network that are being used to make predictions, and if they're doing that consistently. I mean, there are cases where the model may have just identified something you didn't know existed in your data set, right? So even the data set on its own might not be sufficient. There's a lot of sort of backpropagation methods that people use to look at image identification. And sometimes what happens is you'll get prediction on a feature that exists throughout the data set that isn't something in your labels. For example, I saw one example a few years ago where all of the images of horses had a specific watermark in the image, and so it was using the watermark to identify horses or something like that.
Thanks, Sage. Doug, you want to add something on that? Or just...
Yeah, I think one other trend I want to mention here is the moving towards the foundation model. That a lot of those like pre-trained models that people have been trying to put a lot of those different types of data, especially, I mean, large language model is one of the example of foundation model. You're trying to pre-train your very large model and then fine-tune it for a specific use case or applications with a smaller amounts of the data. I know this one has been growing interest, has seen growing interest in Earth environmental science as well. NASA, European Space Agency, IBM, all different players have been entering into the field of foundation models with the, for example, satellite imagery, so with weather and climate modeling. And in that case, that they really directly ingest a huge amount of data that can be like 50 years of the reanalysis fields or the entire archive of the satellite observations, trying to learn the representation of certain features and then trying to, and with a specific small sets of the newly curated well high quality training data that you are able to fine tune that model for a specific use case. And so I see the quality of the data is still very important, no matter is that for the pre-training of the model and then the fine-tuning of it. And I think I agree with Sage that you still need to understand what's the bounds of the those models. And with that foundation model right now, people are still trying to figure out how foundational that is, right? That you cannot really do like all those use cases. So there's really good paper between IBM and NASA. They're trying to identify those like feasible downstream use cases that they can attack with their weather and climate foundation models. They listed a few and then they have reasoning why they do that. So.
Thanks, Doug. Henry, I would like to come back to what you said about the biological variables. So from my point of view, it's very difficult to assess the quality of those data. And what is your perspective on that? Do you expect AI methods to have a better handle on to assess the data, or what are your expectations if it comes to quality of the biological or bioeco data if it comes to AI methods?
Yeah, so it all depends on what the purpose is, which is one of the challenges of working in the context of Goose, is that with Goose, we want to make data useful for as many things as possible, like generalized use. And so, but when you have a specific use case, it's much easier to define what might be acceptable or not. And so when thinking about generalized use for a model that's looking at plankton, for example, that problem or challenge of having enough time and space scope in the data that you're using to train your model, for example, does it actually work during an El Nino, or does it work in the winter, or whatever the case may be? That's sort of for the user to define. And I guess what I'm hoping to see soon is some guidelines about, or community guidance, community-driven guidance on what that looks like, right? How do we describe the kinds of challenges that we were just hearing about, like where the model might work well or not, or what are the boundaries of it? What's the language that we can use to describe that? Because I see that as one of the number one hindrances right now. So one of the models that I was describing earlier for the plankton from underwater microscopes, there's now like, probably about 3 billion of those images right now, and regions of interest. And so what's good enough? So in that case, it's like, it's hard to imagine getting better. and so with millions of trained images, like human annotated images as well, probably close to 10 million, I'm guessing by now, of human annotated, like human expert check. And so, the cases where it's going to be wrong relative to a person using a microscope, it's wildly better with the AI generally, but you will always have these cases of new unseen things coming into the fore, and the machine will try and classify it as something that it thinks exists already, right? So that there are tools you can build into your sort of workflow, including human verification steps, that can try and catch those things. It'll never be perfect, but I think, again, having the community kind of like coalesce on some rules of the road on what might be considered good enough, I think would be very valuable.
Yeah, I agree. Any question from the audience or any comments? So you can always put your question to the question answer box. I would like to come back to this aspect of long-term storage of data. And that always has been a big issue, and people sometimes a bit reluctant to think about this in more detail. So, but Henry, you mentioned this, you raised this issue, and so I think there's this particular aspect. If you do not store the data that you use to develop an AI model, then you're in trouble. So I think that was very good that you emphasized it, that you see this long-term commitment if you work with these AI models. So if I know, Doug, have you at NOAA also considered that, or is this a high priority at the moment, or are you more working on other aspects?
So because with the NCEI, that's a long-term archive, right? It has its like own retention like policy about how different data sets will be like retained in the archive. And I know within machine learning and domain that especially how to link those training data with trained models, and then there are efforts that's going on. I was just in a workshop 2 weeks ago at or a week ago in DC. That's an NSF founded research coordination network looking at the reproducibility and of AI applications. That's one of the aspects, and the training data or the data and the long-term availability of that. It's definitely one of the factors that can impact on reproducibility. And so I think like areas like the Hugging Face and other places have already being able that you can store the data there, but it's a commercial platform, right? And I think there are long-term discussions about long-term data availability. One of the efforts within the US is the National AI Research Resource that is trying to pointing or become a hub where people can identify the resources that's available for the AI development, and that they're trying to link to different repositories that can be used to store or identify those data. And NASA also invested some of the grants to support some of those like archives to archive the training data sets. That it's used to be called Radiant Earth ML Hub, but they recently changed their names to Source Cooperative. That has been putting a lot of those archives of the training data sets being developed. So people don't need to try to recreate training data sets and then just find those data out from the archive to train different models as well.
Okay, thank you, Doug. So I think we should use the final 10 minutes of our session to think about the next steps. And what I heard is that the term community standards from you, Doug, and Henry was talking about building a community as part of DO's. So I think there are right now some activities going that direction. And so the question is how we can, let's say, contribute to that. Shall we have, so to say, some sort of alliance between all those different groups, or how we shall we structure this process? So I'm afraid otherwise we have a lot of activities going in parallel, and I would be good to have a better exchange. So my question to all of you is, how shall we go ahead with this idea of building a community on AI methods? Do you have any ideas? Or
I think one idea would be to separate it into, I know you just talked about joining these things together, to separate it into use cases or different modeling activities, right? Because the bio applications, particularly when you're talking about image recognition models, is a bit different than, I mean, being selfish, the model that I was talking about, but I mean other cases as well. If you're talking about natural language processing, image recognition, I mean, there's these sort of different tracks, and those tracks are largely due to the way that those models were developed in the machine learning community. So the way that you might, I mean, there's sort of this general guideline, right? Like what Douglas was talking about, where house the data, make sure the data has good provenance and things like that. But when you start going down individual paths of pursuing, is this type of model useful for use case X, etc., it should be particular to that approach. Would be my 2 cents.
I like your idea. That's very good. And yeah, Henry, you mentioned DO's and a potential working group there. So how would you see the scope of this working group? Could that cover a broad range, or is it actually more focused on bioeco variables or aspects?
Yeah, so I think it could include both imaging and sound, which are the things that I mostly work with, but also physics, right, and modeling aspects. So those are all parts of DEUCE. DEUCE is a little bit, it would be kind of like out of scope to do atmospheric surface ocean stuff, perhaps. Although personally, I'm a big fan of recognizing that the ocean and Earth are kind of a system together, but DEUCE is focused on deep ocean, as you can appreciate, and so that's maybe a little bit of a boundary, but we can accommodate, I think, a lot of interest, and we are very much about trying to work across the pillars of Goose. Yeah. And so that the opportunity to have some additional meetings using that framework is fine, and then also virtual meetings, but a larger virtual workshop where the attendees, is in the low hundreds. I think was the last we had. That'll be in May. That could be something that includes interactive, something more interactive.
Yeah.
Training and so on. Yeah.
Doug, my feeling is you already established a community within your domain.
I think it's a different. I know probably every discipline or every domain now is talking about AI, so one way or another, and then they're also trying to think about how to establish a group of or community that who are working on that together. And I think more important thing for me to think about is that how to facilitate the cross-pollinations of those working groups or of those communities, especially things that going back to different type of use cases Sage was mentioning, right? Image recognition on satellites and drone and underwater imageries have a lot of similarities, but there's also differences. So thinking about how to facilitate those exchange of knowledge and guidelines, standards, or best practice, what we call it, across the different groups are really important. So if those things are already being established by people outside of the specific group, that can directly be adopted or like modified to better suit a specific use case, So I think that it's more that is something really important to me to think about, those cross-pollination, maybe a super working group of working groups.
I think in data management, we call it a federated approach. Is that right? Yeah. Okay. So, all right. Again, I think, I'm a little bit involved, or I'm actually pushed a little bit for this AI working with induce, and I think that's a good idea to go ahead, and everyone who is participating is welcome to join the discussion. So I'm not sure whether the email distribution list will be available of the participants of this session, but in case yes, then we will keep you in the loop, and in any case, we will make all the presentations available, and it will be in a shared folder. So everyone should know that we are interested to get all participants involved in the discussion, even if there's right now still not that many ideas who are popping up. In any case, so I also like the comments that we heard, and I remember that there was a question about SDGs. I'm not sure whether from George Cummings. Is there anything you would like to add? So you were really pushing for an idea of recognizing SDG 17. Is there anything you would like to add to this aspect? So to say, coming back to the high level goals of AI. If not, I just saw the questions that you raised, and I found it quite interesting. Thinking about also the idea of, let's say, a language model for ocean science, which I also very much like. Okay. Any other comments or ideas? And I think there will be a final session on Friday, and I will try my best to also put some slides together to say as an outcome of our session today. And yeah, at least the other speakers will receive my slides so that they can agree on that. Yeah. Anything else that we have to discuss here or that we forgot? I think we covered quite a big range of ideas. Yeah.
I might just add one quick one. So throughout much of my career, I've heard about how hard it is to store image data, but now we have this agreement with NOAA and NCEI to where they can do that in the long term for the community. Anybody that's working with FathomNet can get access to this. And so what I'm asking is if you have image data that you need to store, reach out and let's test the mechanism, because I think there's a huge demand, and it's sort of like hard to understand how big that demand is. So by testing it, let's test the system and see if it can actually take in this big data set that we know is sort of out there. Yeah.
Thank you very much, Henry, for your comment. So our session will end in 1 minute from now, and I would like to thank all the speakers and all the people who attended the session asking questions. I think we had a very good discussion, and yes, thank everyone, and we keep in touch. Bye-bye.
Thanks. See you.